GLM 5.2 matches GPT-5 on real-world agentic benchmarks at roughly 1/6 the per token cost. It hit 1,524 a low on GDP Valley, a benchmark that measures actual agent work, not trivia. It scored 81.0 on Terminal Bench and 62.1 on SWE Bench Pro, landing within a few points of the most expensive frontier models on long-horizon coding tasks. Those numbers are interesting, but they are not what matters. What matters is why. A 753 billion parameter model should not be keeping pace with systems that have more compute, more data, and more money behind them. The scoreboard says it does. The question is what architectural decisions make that possible. The answer is not one technique. It is 4 techniques that feed each other. And the reason those 4 techniques work is that they attack a specific structural problem most AI systems ignore. Here is how the next 2 hours will unfold. We start with the problem itself. Why agentic loops are so expensive that most systems cannot sustain them. Then we walk through the 4 solutions GLM 5.2 built 2 that cut reading costs, 1 that cuts writing costs, and 1 that fixes how the model learns from long-horizon work. Each one matters on its own, but the real insight is how they multiply. By the end, you'll understand not just why GLM 5.2 works, but why the same engineering principles explain what serious, legal AI needs to get right. An agent is not a chatbot. A chatbot answers one question. An agent works. Watch what actually happens when a coding agent tackles a bug. Turn 1. It reads the error traceback, parses the stack frames, and generates a tool call to open the file at the line that threw. Turn 2. The file contents come back. The agent reads 400 lines of source, identifies 3 candidate functions, and generates a tool call to search the codebase for every caller of the first function. Turn 3. Search results return. The agent reads 8 files, notices a type mismatch in one of them, and generates a tool call to run the test suite with a targeted flag. Turn 4. Tests come back, 3 fail. The agent reads the failure diffs, cross-references them with the type mismatch it found 2 turns ago, and generates an edit to fix the signature. Turn 5. It reruns the tests. 2 pass, 1 still fails. It reads the remaining failure, realizes the fix exposed a second bug downstream, and generates 3 more tool calls to trace that dependency chain. That is 5 turns. Each turn dumps new text into the context window. The tool call, the tool response, the reasoning trace, the next tool call. The context grows monotonically. By turn 15, the agent is carrying 60,000 tokens of accumulated history. By turn 30, it might be past 100,000. And every single turn, the model has to reread that entire history to decide what to do next. Three things make this loop structurally costly. The first is repeated long context retrieval. Standard attention scales quadratically with sequence length. Every token computes a relevant score against every other token. The math is straightforward, but the numbers get violent fast.